So welcome everyone to this advanced C++ course for HPC 2023 edition. We do this course usually every 2 years. This year, since I'm kind of not really hands-on much anymore, so I asked for some help. And here we have the people that actually contributed in alphabetical order. John Middescombe, Fabian Bosch, Alberto Invernizzi, Peter Cardos, Fauzi, Mohammed, Michael Simberg, and Hannes Vogt. Unfortunately, I am the first because of the alphabetical order, Mauro Bianco, but probably I'm the one that did the least amount of work for this year. Here's a brief schedule of the work. Maybe this is the link to the repo. Don't look at it right now. We will give you the slides in some other way. But so the approximate times we go from 8:30 to 10, 10:30, 12, 13, 15, and 15:30, 17 every day. Today we start at 10:30 to allow people from other places to join. And we will provide the links to the slides probably in the event page at CSES. There's also an old repository. This is the one that I used in the past with a lot of examples. Basically, many examples that we have in the slides and other places where basically you can see and try out. But probably right now you can, I guess, wait. But if you want, you search, for example, _C++ on GitHub, and you get the repository if you really want to spend some time there. And there's a lot of examples on little things, all the details that we were explaining in the previous editions. Now this year we expanded a bit to go over to C++ 17 and 20. So there are things that in that repository that are not in the slides that we show here. But I will give you the link of the other material. I would like to start with the survey. Understand a little bit who joined, and let's start by raising your hand if you use the standard template algorithm, library algorithms and containers. How many of you? 3, 4, 5, 6, 7, 8. Okay, they're all in the back. That is strange. How many of you use STD threads instead, for instance, of OpenMP? 1, okay. 2, 3, 4. Okay. How many of you do other types of parallelism, like OpenMP or? Okay. Yeah. Do you use templates? Okay. Okay. Good. Lambdas? There is a group of people there that knows everything already. Why are you here? Const expert, let's go a little bit deeper. Yeah, okay. Always the little cluster over there. Patterns like CRTP, pimple, type erasure. Does this ring any bell? Okay, that's something we might want to mention then. So let's go more on the software engineering. Who does version control, Git or anything else? Oh, this is good. Okay, almost everyone. Do you use test-driven design? So somebody trembling, not very sure. Okay. We will explain why we believe it's important. And this is another question for me. It's like, who develops libraries and who develops applications, I say. So who is a library developer here? So they write software that is going to be used by other developers somewhere else. Yeah, over there. Few. And who are developing applications? So just an application that somebody will use to do something else. There. Okay. This is an important distinction somehow. Okay, let's get into the material. So how many of you come from the university? Is it like postdoc, PhD students or researchers? And how many of you comes from the industry? Okay. And so how many of you are, let's say, HPC people, high performance computing? Okay. Okay, so not many. Okay, that's all right. So the course. So when we designed the course many years ago, the demand was to create a course for the HPC people and learn C++. And it was very difficult because HPC is like anything. So you need to be efficient. So, and now I will have to teach you what do you need to do in C++ to be efficient on a certain architecture? And that's very, very difficult because I don't know what you do, right? I don't know what kind of algorithms you do. And so we always focus a little bit on something else also, which is the software engineering. And this is why some of the questions are here. Because one of the things that we observed is like when we talk about high performance computing, and if you use C++, it's because you care about efficiency. Otherwise, you write in Python or you write in Java, you write in any other thing. But if you write C++, it's because at some level you need the code to be efficient. And now even defining what efficiency is, what high performance means is not easy. What does it mean? I'm using efficiently the functional units of my CPU? Do I care about time to solution? Do I care about energy? Do I care about algorithmic complexity? What is HPC here? Even when we ask the questions like, and I need to teach you how to do C++, then I don't even know where to start. But one of the issues that we encountered here at SCS, right? We are a supercomputing center, so and we provide services for scientists to run simulations, basically. And so what we have observed along the years is that the high performance computing, you have basically two main modes. One is the research codes, right? So somebody, PhD student, professor, researcher comes in and say, well, I want to simulate things in some new way. I need to simulate in a more efficient way. I need to simulate something that was not simulated before. So these are the research code. So somebody sits down and starts writing code and start experimenting. So this is usually research codes that are oriented to study, understanding. So, and usually what you care about that kind of things, like, okay, you need to do short runs just to prove that your idea works. Maybe you want to measure the efficiency by which you can do the computation, how many instructions per cycle you can deliver, or maybe you want to know what is the convergence rate of a certain algorithm. And the results of these research codes is basically something that tells you something about for instance, the computer architecture. How well do you use it? Or even in the math sense, how fast my algorithm converges. We're talking about usually short runs, and the time in which you care about this is basically writing the scientific report that you will publish in a conference or in a journal. Some research codes actually are not oriented to getting just understanding how the architecture is used, understanding the convergence or the mathematics, but it's really you need to simulate something, and you want to run a simulation to simulate a very complex system, and you write the code for it, and then you do it, you do your simulation. In that case, what you really care is about having long simulations. You want to use a lot of resources because you need to simulate something complicated, and the results of these computations are typically scientific. So it doesn't really matter which computing system did that computation, as long as you were able to do it in the amount of time and the resources that you had available, like how many compute nodes or many node hours. And also in this case, though, this might be still researchy in the sense that the code that you run and the output that you get is just valid for the time of writing some scientific report of some kind. But the HPC world also look at production applications, for instance, production libraries. What is production here? Production means that you can reliably provide your software, your application, or your libraries to other people so they can reliably get the results that they need. And usually also this implies that your user of the application will run for a long time. They need to be really efficient in the use of the resources. And also in this case, the results do not depend on the computing machinery. It's like because you need to simulate the system, you want to see if the simulation is right, if the simulation content is what matters. You don't really care deeply if you're using GPUs or not, or if you're using all the functional units at the same time. You just need the simulation to be done. The only reason why you want to be efficient, you want to go on GPUs, is that the more efficient you are, the better you can use the resources, so the less it will cost you to reach those results. And here, the lifetime of these applications is usually very long. You get applications written like 30 years ago, 20 years ago. They're still being used. And the software is still the same, fundamentally. And they span multiple hardware generations. In the HPC world, and you might be familiar with this, is that the computing center you work with decide to change machine, and now you need to go and rewrite or rearrange your code in order to make it efficient there. But if your library is really, or your application is really successful, it means that it has to support multiple hardware generations at the same time, and this is a problem because you need to architect your code so that it doesn't cost you an enormous amount of resources to just support everything. And this is where, let's say, C++ and the software engineering comes in. Because here you can see what do you need to do up there? Well, you need to run something, right? It doesn't have to be super well engineered. It doesn't have to be well architected. Just get the thing down. I need to write a paper about this. So just get me that. And so what you need is that you need to do this in this amount of time. But if I want to be here, I need to think about what are the long-term costs of these things. If I need to increase the number of people a long time to support my software, then it's not scalable anymore. I might not have the money. So, and many times what happens is that people start over there with the research ideas. They write down a piece of code, and then they slowly transition to something that is actually adopted by people. And sometimes being successful is not a good thing. It's not necessarily a good thing, because if you get here and your code is not well architected, then it becomes actually a liability more than a value for you. By the way, if you have any question at any time, raise your hand. So this is my personal opinions here about what kind of people write code. And there are programmers. Programmers are people that usually know how to program a computer and knows at least one programming language quite well, right? So they can write code. They can do application. They can write something. On the other side of the spectrum, in one of the other sides of the spectrum, you have the computer scientist. Who is the computer scientist? Well, he understands algorithm design, like, divide and conquer, dynamic, programming, all things, data structures. Computer scientists understand also the computing machineries, maybe not in super detail, but they understand what they're made of, what are the components, how is it possible that a piece of material can do computation, and also can reason about how efficient something is by doing algorithmic analysis or by even knowing the hardware architecture. And so it depends, what kind of computer science you do. But then also, a computer scientist usually understands what it means to create abstractions. You can abstract something, so you don't see the hardware, you see the programming language, you see, if you are a computer scientist, you kind of have even a feeling with this kind of things. And then there is a software engineer. The software engineer is someone who values the code as an artifact itself, right? You understand, if you are a software engineering, you understand that the software you write is an artifact. You like it, you want to take care of it, right? It's something that you understand on its own value. And also, software engineers understand that the code will need to be maintained for a long time. We need to be refactored, maybe. You need to have a clear design, otherwise it will become a cost instead of a gain. And usually, software engineers like to write code. They like to write clean code. They like to have good rules. They want to see the code and say, well, it looks good, And so these three dimensions, in some sense, so everybody needs to be able at least to do programming. If you want some different level of understanding, well, maybe you are a computer scientist. And if you really want to have your product to work well, you need to be a software engineer. I hope that at the end, all what I'm saying will make sense at the end. So let's consider what is high-performance code, right? This is a matrix multiplication. you have two different versions of it. The only difference is that you have a loop in version up there. Instead of ijk, I go ikj. And by virtue of the commutativity, associativity of the operations, which is not granted because floating points are not, but we kind of assume that they are most of the time, we might say the two codes are basically equivalent, right? They do exactly the same thing, they do it in a different order. And now I can ask you, what is faster? Is A faster? Is B? Or the same? Because, the order, who cares about the order? You have a von Neumann architecture, you don't care. And, or maybe the same just because the compiler understands what I'm doing here. It's able to do the optimizations for me. So who think, hey, A is the right answer? Just out of your guts to say, don't think too much about this. Who thinks B is faster? All right, yeah, okay. And who thinks 3 is the right answer? Right? And 4, who thinks 4 is the right answer? Okay, 4, okay, good. So frankly, I don't know the answer. I haven't told you where this algorithm is going to run. I haven't told you what is the architecture. I haven't told you what type C, A, and B are, because we are assuming in our mind it's like floating point, but this might be something else completely, and I have no idea which one is faster. And so I need to give you more information in order for you to decide which is faster. Usually, if you're talking about floating point operation, probably B is faster, like people here raised to their hand, because we are scanning column major C and B, and yeah, that's a valid argument. That's a valid argument because you are assuming also that this is a C code, then it is laid out in a row major way, which I also didn't tell. And so, well, the bottom line is that if you are doing a matrix multiplication using floating point operation, just use BLAS. Don't write this stuff anymore. You shouldn't. And it's not even always true that BLAS is the best one, because if you have long and skinny matrices, then BLAS might not be the best option for you. But it doesn't matter. The bottom line is that you need to understand what you're doing. So one message is C++ is not writing high-performance code. And again, if you do C++ because you care about efficiency, otherwise you write in some other language. So it's not writing high-performance code easier, but it helps isolating the concerns. It helps you architecting your application, your library, your system in a better way. C++ give you facilities to, for instance, this is a very old slide, right? Think of C++ 14, that this was introduced. You might know, with this, through accessing these values here, you can understand how big your cache lines are, how many, what is the cache associativity. You might understand a few other things, but it's not the programming model. It doesn't tell you how to think. It gives you the tool to do something with your architecture, but it's not that it makes it easier for you to think about this stuff. You still need to know. So you don't want to give to your user, if you are a library, your user shouldn't be able to touch this kind of stuff. It is you that you need to do it and give to your user the best solution given the information that you have. So now the question is, what is C++? It doesn't make things easier, so why should we use it? Well, C++ allows you to generate or implement overhead-free abstractions. So you can provide abstraction layers, so the user of those abstractions see the word in a different way than you do, right? So you see the registers, you see the memory, you see the cache. The user sees, oh, how beautiful, matrix, matrix, multiply, right? So we build abstraction layers. Overhead free means that you can really, in many cases, avoid any overhead, but given the constraints you might have on some other side, there might be a small one, but still, you can control it. You can have a good abstraction mechanism. And also it allows you to develop safe code, robust and safe code. You can build large applications in C++, large systems, large software systems that are robust, reliable. They never break. In order to do so, you have to do something. You need to learn how to do it. It doesn't come for free. For instance, one of the things you want to do is to use RAI. We will talk about RAI. Resource allocation is initialization, which is made possible in C++ 11 onward, and allows you to really have safe code in the sense that you don't have pieces that stays there. For instance, you can remove the problem of the memory leaks and having resources that stay there and you don't know about. So yeah, in order to do this, in order to develop safe and robust code, you need to act on it. You need to do something on it. So why do you need C++? Why do you want to use C++? Well, it is supported by the hardware usually. The first thing a hardware vendor does is support C++ compiler, usually. It is integrated in IDEs. Why? Because there's a lot of users, a lot of industries rely on C++, so the development environments are actually quite solid and quite good, enjoyable even. And you have available compilers. And the good thing about the C++ implementation roadmap is that before entering into the standard, there should be at least a couple of implementations that actually show the thing works, which means that once a standard is available, you almost immediately have the compiler that supports it. Not for all the features, but many of them. You have the online community. You go to Stack Overflow. You ask a question, right? Hopefully, Stack Overflow will remain around and not be replaced by AI. Let's see. And your application, your library, your software system scales with the complexity. You can make it as complex as you want, fundamentally. And you can control the investment you make by really make the right decisions about isolations of different pieces. And you can design with C++, which is different from C and Fortran, for instance, is that it allows you to really do API design. So the application, so the function interfaces, the different components, you can define how they talk to each other, how the user talk to these components in a very robust way. And thanks to the overhead-free abstractions, it's not only you can do it, but it's actually efficient. Because you can always do a good interface. You can always have an interface which is beautiful, but it might be extremely slow. And in C++, you can have good interfaces, you can have great interfaces, or even horrible interfaces, but they will be efficient. So C++ allows you to raise the level of abstraction without compromising on performance. And these lead to declarative style programming. What is declarative style programming? You tell the computer what to do and not how to do it. In the algorithm that I showed you earlier for the matrix multiplication with the loops, you are telling what to do, even though you're not telling how the operations are going to be done, but you're telling how those operations need to be executed, in which order you are expecting them to be executed. While at some point you want to say, well, I need to do a matrix multiply. I don't want to know more about that. Somebody else will take care of how, but I just need to need what I want to do. I have a small example here that I've been working on. I'm pretty sure it will be maybe shown also other times during this course or something similar. I have no idea. You do what you need to do. So let's say that I have a function that computes a Laplacian. This is written in Python just because I'm lazy, okay? And I needed to show that it actually works. So we can concentrate on the body of the loop there, right? It computes, it allocates the output array. So I get the 2D array as input, and I compute the Laplacian in the 2D array as output, and the 2D array is allocated inside and put back into the output. So now this is how a C++ person would write this, right? It's two loops and you do the thing inside. So it's not how a Python person would do it, right? A Python person would write a single line for this thing. But, in C you will write something like this. And now you want to call the Laplacian of the Laplacian. So this will work, and this is the reason why the first line looks a little bit complicated. And you can compute the Laplacian of a 2D array, of a 2D field. The problem with this is that it could be slow, because first of all, I am allocating something that goes, the output of the first Laplacian that goes into the input of the other one. And I'm doing too many road trips to the RAM, because I need to read X, write Y into RAM, then the next step, I take Y, I read it from RAM, do my computation, and write the output there. So I'm doing 2 round trips to the RAM for the whole field. So if the field is big, it's going to cost you. And so one can do, and this is what you can find sometimes in scientific application, well, you do fuse, you just fuse. You create another function, which is lap2. Sorry for my limited ability to find names. But I have lap2, and lap2 computes the Laplacian of a Laplacian. And this is how the code will look like. And this might be faster. So this is Python, so it's not faster. But in C++, you might say this is faster because I read X, I do my computation, I just write Y once. I have only 2 round trips. I still have the allocation there. Let's suppose it's fine, right? This is more efficient. But now I'm telling you, well, yeah, you should go there. There is a bug. Please find it, right? Yeah, it's a bit scary. What if my application have 20 different stencils? This is called stencil, by the way. I hope no one is surprised by that, but if you raise your hand in case. So now I have one application which has like 20 stencils, and they appear in my application in many different combinations. And now what I do? Well, I need to have a lap2, I need a lap with the other thing, I need a function that pair these are the 2, and maybe I want to pair 3 at a time, right? Instead of only two stencils. And then you start having like an enormous number of functions that compute efficiently all the pairs. And now you see, if you want to maintain this code, something's wrong, you need to fix a bug. It's very difficult. You don't go back easily to the 2 Laplacians once you have written this. It's too late, right? You have used it, and now I need to go back to a simpler thing. Oh, well, I need to understand what the hell these people wanted to do in the first place. And if the name of the function is like the one that I chose, I don't know. All right, I might not be able to find it out easily. So, what do you want to do? You want to raise the level of abstraction. You want to allow for the efficiency to be there. And this might require quite a bit of tooling, quite a bit of rework of your code, of the concept in your code. And this is why you need to know the language well if we want to really to address this kind of things. C++ offers also what is called library adaptation and library abstraction. So I have a library for doing image processing, and then, well, I have another code that uses another library, but I know that this guy is doing what I need, but the interface is weird. Well, I can provide a layer that abstracts this library, changes its interface, and I can use it without changing my main code. So in some cases, you can do something like that without overhead. So you can do adaptation. You can separate the constraints, my matrix multiply. That is efficient. I don't need to touch it, or somebody will do the optimization. I just need to call it. So somebody is responsible for the efficiency, somebody is responsible for the use. You can have fast prototyping. You can write code and then slowly migrate it into the final application. Not easy, but can be done, right? Or anyway, the refactoring has always to be put into the conversation. At some point, you need to refactor your code, but it is possible. C++ offers you tools for doing that if you design your interface in the right way. Incremental optimization is, for instance, I'm using my matrix multiplication function, and somebody over time will make it more and more efficient. For me, I don't need to do anything. Some of the traditional HPC tools, I mean, inside the scientific computing area, would not work very well, because C++ uses massive inlining. This is the major engine, let's say, that C++ has to do these overhead-free abstractions is massive inlining. So it lines everything that it can. You might write a very long code that at the end is just the main function because everything is being inlined. And now if I want to understand what's going on in there, I need to know how many times a function is called. I might not even see that function anymore. So some of the tools will not work very well. But I would say nowadays it seems to work quite well. So why do you... I hope I was able to tell you why you need C++, what it can do. I didn't tell you how yet. But, you know, this is why we're having the course here. But it should be also clear that you need to be active in this thing, right? The C++ doesn't make your life easier. There's a saying in the C++ community that C++ allow you to shoot yourself in the foot. And you need to be aware of this, right? It's not always easy, it's not always simple, but it allows you to do great things. So, in order to do good C++, you need to know how to handle it, how to manage it, how to understand it. And so you need to do API design. I will talk more about this, but designing the interface of your functions, your classes, is really fundamental. You need to do it right. You need to test your code. You need to be sure that the little pieces that you write works, so that when you compose them, also the composition should work, right? It's not automatically true, but you know, at least you have a baseline. And you need to do test-driven development. I will go into this a little bit further on. I've been talking already for a lot of time. I told you it will be like 40 minutes, right? I'm already at 40 minutes, so it's going to take a little bit longer. So you need to have systematic application of methodologies. You need to stick to the rules. You need the coding standards in order to make your code readable by you and by other people. And so the course is in this context. You're not only here to learn about C++ features, language, how can I use those features, how can I use the language in order to produce something which is solid, which is maintainable, which is efficient. But to do so, you need to understand, I think, also these points over here. So everything should be tested, right? So there are only a few things that cannot be tested. But if you have a function, if you have a class, if you have a class with an invariant, you need to test that the invariant is always valid. You need to check that the function produces the value that you care. C++ doesn't offer a testing framework. That there are testing frameworks out there, and we had Fauzi will go into these kind of things. But you know, there are tools out there you can use. In the scientific code, I was assuming most of the people came from the scientific computing background. And in the scientific case, testing might be tricky, right? You are testing something you don't even know if it exists, right? You're running a simulation of something that no one did before. How do you test it? It's tricky, very, very tricky, but at least the basic blocks should be tested, right? The basic things, so then you can grow up there. And you might get, into issues that if you want really to test your application, you need a lot of resources, so you cannot run automatic tests at every pull request because GitHub doesn't give you the amount of resources, doesn't give you the hardware to do so. And maybe in order to really know if your application works, you need to do uncertainty quantification, and that takes more resources than running simulations right now. So it's very difficult. And so testing, yes, as much as you can, and then be reasonable. So what is test-driven design? It's like before you write anything, before you write a function, before you write a class, before you write the implementation of something, you write the test that proves that the thing works as you expect. This forces you to think as a user and leads kind of automatically to good interfaces or better interfaces. Because if you start from the implementation detail, from the algorithm, because it's the thing that you really care actually, if you start from there, then the interface might come up a little bit fuzzy or not clear enough. But you think like a user, say, I need to use this, how do I need to use it? And that you write the test, and only after the test is done, you develop the feature. It's not easy to do, because you're always tempted to go into and plug and write the cool stuff first. Because in some sense, and this is a teaching that I'm taking with me since many, many years, is that we are all API designers. We are all designing interfaces. The interfaces is the most durable thing you write. One of the worst things that can happen is that you write a code with a bad interface that is adopted by a large community. That's horrible, because now you cannot change it anymore, or it will take a lot of effort to do so. So what do? Well, you start as best as you can. You write the best interface that you can so that in the future you don't have to change it because it doesn't work anymore. It is very, very tricky. But so APIs are really important. I also usually do desire-driven design. So I think about how would I like to use it in the best word. If I had the best language in my hand. And then I work out the details around it. And sometimes this gives you quite nice interfaces, and sometimes it fails too. And so the idea is that is the KISS idea, which is to keep it simple, stupid. Like, don't over-engineer, don't make things over-complicated, but know where you are going. So a good API. What is a good API? You are all API designers, right? We established that. I established that for you. And now, well, they need to be easy to use correctly. Right? You should not be making mistakes just because you don't know what's going on. It should be self-explanatory. Let's say I have a list data structure, and I have a list size and a list real size. Can you tell me what these two functions are doing? Somebody wants to try. What if I rename these two functions list length and list maximum length? Okay, maybe now I understand what's going on here. This is the length of my list, I assume, and the maximum length is I cannot grow the list bigger than this size. But if you use the other names, you might get confused. And it happens all the time. We need to check for error conditions and signal the errors in the right way. Now, there are many tools in which you can do this, but asserts, exceptions, error codes, static asserts, we'll see. So there are many ways. It's very difficult to decide for a good error handling because, it's not an easy decision to make. But also, it is easy to use correctly, but difficult to use mistakenly. You shouldn't be in doubt. You shouldn't make a mistake that, if it is an obvious mistake, it should be caught. Or it should be clear to you, how should I not use something? So, and one may say, well, I have my API. I have written three HTML pages about list size and list real size. People should go there, read that before using my API. And I guess you know that you're not going to do it. So your users even less. So, tricky. You need to adhere to rules. So RAI, again, will be explained later on. Super important. A programmer should never write a new statement or a malloc statement in the code. Somebody has to do it down into the pit, but as the user are at a higher level, they should never be able to do. They should never need to write that kind of code. And there are other rules, like, okay, well, I need to write at most, every function should be at maximum n lines of code, how many things a class should do, things like that. The important rule is to write the code that comment itself, and only fix the code, only comment the code when it is not clear. But the code should be something that people read and understand what's going on. And this is why you need, if you work in a team especially, do code reviews. Let somebody else look at your code and they tell you if they understand or not what they are saying. Okay? And stick to the rules. I think I skipped this one. This is what is wrong about this code. And there's a lot wrong with this code, but I don't want to spend time on this one. So function design. How do if I have a function that I call set time, and the first argument is the year, the second is month, and the third one is day. They're all integers. And I call set time 10/7/2012, and What does that mean? What is the 10 and 7? Am I sure that I'm passing the day? 10 is the year, 7 is a month, and 2012 is the day. There's no check here in the interface. They're all valid integers. I pass these numbers. So instead, I can use, in C++, you can define the types. This is kind of a silly example, but just trying to convey the point, is that I can do day 10, month 7, and year 2012. When I call my function, which accept a day, accept a month, and accept a year, this will give me a compilation error because it cannot convert day to a year type, right? So you cannot use it in the wrong way. And don't provide the conversions between day and month, for instance. You know, be to this respect the rules that you set for yourself, and maybe call it set date instead of set time. So we at least know that we're not talking about hour of the day. The rule of 0, rule of 3, rule of 5, this will be discussed later on, if I remember correctly, right? Method RAI will also be discussed. Coding conventions, very important. Use coding conventions. If m_name, if I see m_name, for instance, I know it is a data member of a class. If I see an n with a capital letter, I know it is the name of a template argument. Now, this is just one example, of course. But, you know, don't be too strict to it, because otherwise you end up in hours and hours of discussions about do you want to do underscore, do you want to use camel case or not, which is usually not very productive. Design patterns. So C++ provides you a lot of design patterns like factories, RTP, type erasure, proxy, adapters, visitors. I mean, there are so many different patterns you can implement with C++. Many of them you won't need, but some of them you might need. Some of them are actually good, some others are not good. Singletons, for instance, you should try to avoid. CRTP also, but you know, they are there. And be familiar a bit with this kind of strategies. It basically tells you how you need to architect your classes in order to reach some goals. So why you need to do this? Because you don't want to reinvent the wheel every time. You can, oh, I discovered a way in which I can avoid passing the type of something into, yeah, already done, okay? It's very difficult to invent something new in this language. So the schedule is like, this is my introduction that I've been giving here. The schedule will move around things. When we have slots, we can squeeze in things. But we basically start looking at the infrastructure, the tools you have available, some of the RAI stuff, essential utilities, generic programming. This is an important topic that basically underlies almost everything that we do here. And tomorrow is more like, again, std functions, lambdas, function objects, generic programming, again, how to understand things, how C++ decides to call a function instead of another, templates. We go into concepts, we go if const expr, and a few other things that helps you write code that is easy to read and, well, easy to read if you know C++. But it's easy to read and that you can actually understand exactly what's going on. And then we go into examples too. So we show you examples. We try to get some exercises that you can try to put your hands on. And we go, data-oriented. Design, we go into understanding, how the data is laid out in memory, how can you use it more efficiently, more like the HPC, Word. Other examples, many of those are from what we are involved here at CSCS. And then, let's say, a discussion about future of C++ and some Q&A. I would like to close with this slide here. So some behavior in C++ language might look a bit complicated or unclear. So why does this happen, right? When you look at the output of the compiler and you see like long lists of things that is not right in your code, and you say, why is it that so difficult? Well, there are reasons why. Some reasons are due to backward compatibility, for instance, to older versions of C++, and others because the language is tricky, because there are features that are difficult to implement in the right way. But what I typically do is that since these things have a reason why they're there, right? They're not there because some lunatic came in and said, oh, this is the rule now. No, it's because there is a reason why. Okay. And so understanding why, to me, is usually important because I need to understand how a thing works in order to remember them. Otherwise, I will forget. So we need to have a mental model. It's like, how do we reason about this? Why is this choice made like this? How can I really interpret it? And to do so, you need, I think, but it's absolutely up to you, I guess, to know a little bit how the language actually is then compiled into an executable. Understanding how virtual functions can actually be implemented in the real world is not that easy. I mean, how is it possible that at runtime I choose the right function, you know, or how is that like even called recursive functions, for instance, if you think about it. So you need to know what this function, how a function is called, what is stack frame, what does it mean to optimize the code, what allows me to optimize the code and what doesn't, what does a compiler can assume in order to make optimizations and what cannot. And there are different things you can really, for instance, another thing is that when you compile your code and you're trying to look into the executable for the functions that you wrote, right? There is a place where the object file contains the name of the function that you actually wrote. And you go there and you look, this is a very strange name. So you see the name of the function there, but around there's a lot of other symbols and things. And say, what's going on? Well, to understand that, you need to understand something like Goderization, actually, which is the process by which you can take some abstract concept and you turn it into a string. You don't need to go into all of these details. I believe that if you understand a little bit what's going on there, it becomes clear why the compiler make certain choices. And sometimes we can live just with approximate models just to help our mind to make sense of what's going on. But with this, this is my last slide. So thank you for listening. And if you have any question, feel free to ask. Otherwise, we can go on with the next thing. It's a few fuzzy.